Welcome everyone. This is our 6th annual Turfe Lecture. So these lectures are made possible by a generous donation from Al Turfe. So let's thank Al, who is right over there. And it's my pleasure to introduce Professor Eugenia Cheng, who's scientist in residence at the School of the Art Institute of Chicago and honorary fellow at the University of Sheffield. Professor Cheng earned her PhD from the University of Cambridge in 2002. Her thesis, Higher Dimensional Category Theory, Optopic Foundations, was completed under the direction of Martin Hyland. Alongside her research in category theory and undergraduate teaching, her aim is to rid the world of math phobia. Professor Cheng was an early pioneer of math on YouTube, and her videos have been viewed over 10 million times to date. She's also assisted with mathematics in elementary, middle, and high schools for 20 years. Her first popular math book, How to Bake Pie, was featured on The Late Show with Stephen Colbert, and Beyond Infinity was shortlisted for the Royal Society Science Book Prize 2017. Copies of these books are available for purchase outside. There's a table right outside the door, and Professor Cheng will be signing copies after the talk if you would like a signed copy. She also writes the Everyday Math column for the Wall Street Journal and recently completed her first mathematical art competition for Hotel EMC2 in Chicago. She's the founder of the Leaders Tube, an intimate oasis for art song based in Chicago, and her next book, The Art of Logic in an Illogical World, is due out in 2018. And as we'll hear today, Professor Cheng is also an accomplished concert pianist. So without further ado, our Turfe Lecture for 2018, Professor Eugenia Cheng.
Well, thank you very much for coming, everybody, and thank you for making these lectures possible, and thanks for the invitation, everybody. I'm very glad that you're all here to hear me talk about math and food today. And many people ask me why I wrote a book about math and food, and the answer is that I love math and I love food. And unfortunately, most people seem to love food more than they love math, and so I decided that I would like to share my love of math with everybody via food. Now, I think that most of you already love math. And so what I want to show is that it is possible to share very high-level mathematical concepts, even to people who don't know any math, have forgotten all their math, are afraid of math, think they can't do math. Because I've been teaching math to art students at the School of the Art Institute of Chicago for several years now, and many of them failed high school math or have forgotten all of the math, and they think that math is not for them. And I teach them a course on math, abstract math, not remedial math, not numbers, not times tables, not solving equations, but math as a way of thinking. And they find that they realize it's actually relevant to them because they do like thinking. Whereas when it's numbers and equations, they think, oh, that's for other people. That's for scientists and engineers and people working in finance. That's not for us. So I think this math is for everybody. And I was very lucky because my mother showed me many wonderful mathematical things when I was little, so that I knew that no matter how bored I got in math class at school, math was something more exciting than those things, those endless questions and tests and right and wrong answers. But I know that most people don't have someone in their family showing them cool math at home. And so I've decided to be that person for everybody and show ways that it'd be great if we can reform the whole education system so that we can teach math in much more interesting ways all the way through education. There are some wonderful math teachers there, and some people get to have a wonderful math teacher who shows them wonderful things. But in the meantime, while we're working on changing the entire system, I've decided to write books to show everybody the things that I really love about mathematics already. Some of these things are things that I didn't see until I was doing my PhD in category theory, and things that you would usually not see unless you do a PhD in category theory or maybe topology. And usually to get to that point, you have to pass endless rounds of tests and more tests and quizzes and exams and then more qualifying exams, and finally you get to make up your own math and see these things. So I've just decided to shortcut that system and show everybody those things right now. So I am going to show you some of my favorite mathematical structures today, including some Bach, juggling, hair, factors of 30. Those are mathematical and are related to, we saw some of that in the session this morning, those of you who came to that, cake, and custard. And one of the reasons I started talking about math via food is because I love telling stories when I'm teaching math, especially apparently random stories that turn out to be related in surprising ways. And I realized that every time I told a story about every time I told a story about food, my math students kind of woke up. And this is not to say that they were asleep exactly beforehand, but they kind of perked up. And I realized that I could tell some math story using food practically about anything. And one day, I turned up to my usual group theory lecture, and there was a random plate of Oreo cookies on the front desk. And someone called out, "Use it to explain some math!" And so the students thought I had brought them Oreo cookies, and I thought they had brought me Oreo cookies. We never figured out where the Oreo cookies came from. But I looked at them and I thought, you know, we're doing conjugation today. And if you've done conjugation in group theory, then you know it's about multiplying something by the same thing on each side. But one of them has to be inverted. And students often forget that one of them has to be inverted. It's an Oreo cookie. You have a cookie, and then you have some cream filling, and then the other cookies the other way up. And this started a whole chain of ways of explaining math using food that I've continued throughout this entire book. So first of all, in order to show what my mathematical structures inside these things are, I need to tell you what math is to me. Because you know that it's not just about numbers and equations, but what is math? And I start every math course I ever give by saying to everyone in the room, what is math? And it's surprising how horrified people look that I've asked them this question. So what is math? I think that math is the study of how things work. But not just the study of how any old things work. I think that math is the study of how logical things work. But it's not any old study of how logical things work. I think it's the logical study of how logical things work. And the trouble with that is that nothing does behave logically. I don't behave logically, probably even you don't behave logically all the time. The computer doesn't behave logically. The keyboard hasn't been behaving logically. Things just don't behave logically in the world. So in order to study anything logically, we have to forget the pesky details that stop them behaving logically. And that takes us from the real world into the abstract world of ideas where things really do behave logically. And in that process of abstraction, many different things become the same. So you start with maybe 2 cookies and 2 chairs and 2 people, and then you go, something's going on. What do these situations have in common? If we forget the fact that they were cookies or chairs or people, we have 2 things, and then we get the concept of 2. And that's how numbers come about. Numbers are already abstractions from objects. But we mostly performed that abstraction in our heads so long ago that we've forgotten about it now, and we're very comfortable with numbers. But if you try and help small children learn to count, and I love doing this, you have to keep showing them objects and counting out loud and just wait until they make the connection between these strange words you're saying and the objects that they have in front of them. And that is a leap of abstraction that people take more and less time to make. And every time we do a leap of abstraction during the course of math education, we lose some people. They fall off because they are unable to make that leap. And often it's because they don't know why they should even want to make that leap. And people often say to me, I was fine with math until the numbers became letters. And no one ever maybe pointed out to them that the reason they become letters is so that we can be more lazy, so that we can study lots of different things at the same time without having to do the same thing over and over again. And I say that math comes from being lazy. I got into trouble this week on Twitter, as I often do, for saying that, because someone said we should tell everyone they shouldn't be lazy. This is terrible. But math comes from being lazy in a good way, not wanting to just cut corners and forget things, but wanting to become more efficient. So if you do something the same time, if you do the same thing several times, you go, wait, I don't want to do the same thing several times. I'm going to make a theory that will do it for me. And that's what math is. So the other thing about the abstract world is that you don't really have your feet on the ground anymore. You're kind of floating around in a world of ideas. And this can be disconcerting, which is why I tell lots of stories and make analogies to try and show how we're feeling about it via things that everyone already knows how to feel about. Because when in the abstract world, you have no actual life experience of it, so you don't know what to feel. So I make connections with things that we can all feel things about. The thing about the abstract world is that things behave according to logic, which means that you can only reason according to logic. So some people like winning arguments by yelling. They do not like the abstract world because you can't win arguments by yelling in the abstract world. I don't like winning arguments by yelling. I could. I'm very loud. but I don't like doing it. I prefer reasoning about things using logic. So my first mathematical structure I'm going to show you is about a piece of Bach. And I know that Professor Fiore does a lot of math and music, and that some of you have probably studied those things. So I'm going to show you a mathematical structure inside one of my favorite pieces of Bach. As I'm sure you know, there's tons of math inside Bach, and I could talk about that for several weeks without stopping, so I won't do that. I'll just tell you one thing. So this piece is from the second book of Preludes and Fugues that Bach wrote. During Bach's time, it became possible to tune instruments better than they used to be, that has math in it as well, in such a way that you could play in every key and it would sound all right. Before that, some keys sounded great and some other keys sounded disgusting. So you had to kind of pick a key and stay in it. But it became possible to tune it so that every key sounded quite nice. And Bach got excited about it, and he wrote a piece in every key. They're called Preludes and Fugues. So there's 12 keys on the piano. That makes 12. There's major and minor. So he did major and minor, which makes 24. Then he got really excited and did the whole thing again. So that makes 48. And this one is the Prelude in G minor from Book 2. And I'm going to start by playing it for you. Thank you. Thanks. Now, like many pieces of Bach, this is written in polyphony, which means that there are several lines of music that wind their way around each other. And in theory, you could get some people to sing it, and each person would take one part. And so here, the first person would just start going, bum, and then the next person would go, do-do-do-do, do-do-do-do, and then someone else would come, da-da-da-da-da-da-da-da-da-da. And what you usually do when you start studying a piece of polyphony is that you play each part individually to understand each one by itself first. And when I was studying this piece, I found that I got confused when I tried to do that, and I couldn't follow where the parts were going. So I decided to draw a picture of it, and the picture came out like this. So you can see that the black line at the top kind of creeps its way down, and they all cross over each other. And when I drew this picture, I understood why I didn't understand. And that's always the first step to understanding something. And the reason I didn't understand it was because these parts cross over each other and they don't come back again. So I lost them, and I became confused about where they were. And that means if you were trying to get a soprano, alto, and tenor and bass to sing this, it would be a bit difficult, because the soprano starts at the top and would have to end up as a tenor, whereas the bass, who's the red one, has to go up and end up as the alto, and the green alto ends up as the bass, and the blue tenor ends up as the soprano. And I do have one friend who can sing soprano, alto, tenor, and bass, but that's a bit unusual. And so usually they have to stay in their own places. So this is a very extreme abstraction of the piece of music, where I have forgotten almost every detail apart from where the lines of music are in relation to each other at any given moment. And this abstraction helps me to play the piece better, because I understand what the abstract structure is inside it. Now, you don't have to know that this picture is there in order to listen to the piece of music. And that's just like a lot of the math around us. There's math everywhere around us. We don't have to know it's there in order to live our lives, right? We don't have to know where the structural walls are in a building in order to use the building. But it's a good thing that someone knows where the structural walls are. And if we do know where the abstract structures are, then we can understand a situation better. We can use it better. We can fix it if it goes wrong. We can make up our own versions. It's like the fact that if you're cooking something, you can follow a recipe. But if you understand the recipe, then you can modify it according to your taste and understand how to change it and make up your own recipes without everything going wrong. And I think that math is a lot like cooking, because you take some basic ingredients, do some stuff to it, and see what happens. And in the end, in the kitchen, if you're cooking for yourself, then the fun part, I think, is where you stop following someone else's recipe and make something up for yourself. And then all you have to do is decide if it's delicious or not. The worst that happens is you poison yourself, maybe. And in math, I think the fun part is when you start making it up for yourself as well. And I say to my students, the worst thing that happens is maybe you cause a contradiction and then your world implodes. But that's OK. It's an abstract world, so you can just try again with another world. It's not like in the real world where something actually really might go wrong. So this abstract structure helped me understand this piece. And the interesting thing I find, well, one of the interesting things is that I didn't think of this as a piece of math when I did it. I was a master's student at the time. I had not started really studying category theory deeply. And then when I started my PhD, one of the first papers that my supervisor gave me to read had pictures like this in it. It was about braided monoidal categories by Joyal and Street. And it has these things in it, and they're called braids, and mathematicians study them as mathematical structures in part of topology, which is studying the shapes of things. And they study things like how tangled up they are and where the crossings are. And I just didn't realize it was a piece of math. And there's a lot of math out there that everyone is doing all the time without even realizing it's math. A lot of people think, oh yeah, I do math when I calculate the tip on a restaurant bill, or when I work out my taxes. Those are the most boring types of math to do. There's all this other stuff that you don't even realize you're doing. And the same is true of category theory, which is my field. You may be doing category theory already without even realizing that you're doing it, just like with this. So these structures are related to juggling. Now, I used to say, I'm terrible at juggling. And then someone said to me, you know, that's like what people say about math. And I went, oops, yeah, it is, isn't it? So I'm OK at juggling. I'm not that great at it yet. And I'm not that confident about doing it in front of an audience. So I'm wondering if there's someone here who will do a juggling demonstration. Hooray! Thank you very much. Big round of applause. What's your name?
Kyle.
Kyle. Thank you very much, Kyle. Just normal. Woo! Now, would you mind walking across the room while you do it? Mm-hmm. There's a big podium in the way, lectern in the way, but. Now, I'd like you all to imagine that we have a long exposure camera. So we're going to take a picture of Kyle as he walks across the room with long exposure. Each ball is therefore going to make a path through the air. And can you work out what picture that is going to be? Can you do it one more time? Thank you. Thank you very much. Woo! Thank you. So here is a picture that I made using a long exposure camera and some illuminated juggling balls in a dark room. It was not me doing the juggling. When I tried it, it was extremely wonky. So this is an 8-year-old boy in a school that I was helping at. Here's one I made digitally, so you can see exactly what pattern it makes. And now we get the hilarious slow motion version of the juggling demonstration. So if I start with the green and the red balls in my right hand, the green one goes across. As the green one is going across, the blue one comes underneath it. And as the blue one is going across, the red one comes underneath it. And as the red one is going across, the green one comes underneath it, and so on. And if I turn it this way, you can see it's the same as the braid in my hair. Now, I once tried to braid my hair in the Bach braid. You might be able to tell it doesn't work at all. You need so many bands to hold it in place. That green strand is just floating around doing nothing. So is the black one. The red and the blue ones are looped together, but the rest of it's just doing nothing. So you can see for the normal braid, it really is so looped together that there's nothing that can actually move, which is why you can really hold it in with just one band. And if I take the band out and then pretend I'm in a shampoo commercial, which I really wanted to do when I was little, you can see it really was just held together by one band. So this is something that topologists study about braids. How tangled up are they? How much can you wave around one strand? If I pull that green one across here, what's the braid going to look like? That counts as the same in some sense because you haven't really changed how tangled up it is. You're just looking at it from a different angle. And so mathematicians studied these because it's interesting. But it later turned out to be useful in many ways. It's useful because of something to do with how maybe robotic arms move. It's useful to do with figuring out when computers are going to crash. It may be useful for the early diagnosis of Alzheimer's disease, which might be caused by brain cells getting tangled up in the wrong mutated way. And now you can't just stick your finger into someone's brain and wave a brain cell around to see whether it has become the wrong tangle. And so math gives us abstract ways to study these things without having to poke into somebody's brain and fiddle around. Because I couldn't make this into a braid in my hair, I made it into a pie instead. This is my Bach pie. It's banana and chocolate. So now on to something that is more obviously mathematical, the factors of 30. And you know about this if you came to the session this morning. So we can write down the factors of 30. Maybe you can remember what they are. They are 1 and 2 and 3 and 5, 6, 10, 15, and 30. Very good. It's not very interesting. And my art students are not interested in factors of numbers at all, or at least they weren't. And then I say, well, we can find some more interesting things about these factors because we've just kind of written them in a one-dimensional straight line, which is an accident because we live in three-dimensional space. We write on two-dimensional pieces of paper, and we write them in one-dimensional straight lines. And I already told this joke this morning, but I'm going to say it again, which is that this is why I don't like tidying the papers on my desk, because they have natural geometry in 3 dimensions. They don't want to be stuffed into a one-dimensional straight line. And a lot of math has natural geometry in higher dimensions as well. I would say that. I'm a higher dimensional category theorist. But maybe actually that's why I'm a higher dimensional category theorist, because I like finding the natural geometry in higher dimensions. So we can find the natural geometry of this situation by now writing down which of these numbers are factors of each other. And we can draw a kind of family tree that shows those relationships. And like with a family tree, we don't need to draw lines between 2 generations. We're just going to draw them between successive generations. So 30 is at the top like a kind of great-grandparent. 6, 10, and 15 go straight into 30. 5 goes into 10 and 15. 2 goes into 6 and 10. 3 goes into 6 and 15. And 1 goes into 2, 3, and 5. So now we see that it's a cube, which is a bit more interesting than a bunch of numbers in a straight line. And this is an abstract structure that we found by examining the relationships between those numbers. And category theory does a lot of examining the relationships between things rather than their intrinsic properties. Now, we can actually relate this back to the braids that we were just talking about, because if we take this very seriously as a cube, then we can wrap it up with ribbon as if it were a present. And I'm going to wrap it up like this, and I'm going to invent a rule. We can invent rules in math. A lot of people think math is about other people's rules that get imposed on you. But when you're doing research, it's about making up your own rules, which is much more fun. Who likes following other people's rules? I certainly don't. So my rule is that the ribbon coming in from the right is going to be on top. So I follow this down the side, and I need one more color of ribbon to come in on the other side. So that's going to be green, and it's coming in from the right, so it's on top. Now I'm going to do the same to the other half of the cube with the same colors starting in the same places. And this time it's going to follow this pattern. So the red, blue, and green ends are in the same places. But because we have a different configuration of squares, it's now going to look different. And now I hope that you can see, if you kind of shuffle this green strand up and push the red and blue crossing down, the one on the left turns into the one on the right without us having to move the ends at all. So in terms of the topology of it, those braids are the same thing. And this is some fancy piece of topology called the third Reidemeister move. We give things fancy names in math to make ourselves feel clever. And the Reidemeister moves are saying, what is the smallest number of moves that we can use to build up all the possible ways of transforming one tangled up thing into another? So the first one says you take something that's looped around and you pull it straight. The second one says you take two things crossing like this and pull them straight. And the third one says that. The squares in the background are a piece of higher dimensional algebra that also has a fancy name. It's the Yang-Baxter equation. But it's really two halves of a cube. And the fact that those are related was also something that I met while I was doing my PhD. And it's become a fundamental part of my work because it crops up in many places. And then I thought, hey, wait, what about that Bach braid? So what we've done here is we've taken a present and we've wrapped it up with ribbon. So how about we take this ribbon and we reverse engineer a present that is the exact correct shape to be wrapped up by this ribbon. So we need one square face for every crossing of ribbons. And that means there are 6 crossings, there are 6 faces. And I stared at this for a while and I thought, crikey, it's a cube. And then I thought, wait, what? And so I frantically tore up some sheets of paper and stuck them together and made a really wonky cube and drew lines on it. And it really was a cube. And so then I did exactly what I do whenever I prove a mathematical theorem, which is I went, and then 2 seconds later I went, I'm probably wrong. And then 2 seconds after that, I went, I bet everyone in the whole world knows this apart from me. And then 2 seconds after that, I went, it's probably trivial. So I checked it's not trivial, which is to say not every braid produces a cube. You need 6 crossings to have 6 faces. So then I thought maybe every 6 crossing braid makes a cube. And it doesn't, because you can just go take 2 strands and go cross, 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 and that will not be a cube. I don't know why this is a cube. I called my friend, the one who can sing soprano, alto, tenor, a bass, and I said, oh, it's a cube. And he said, I think this shows that Bach was communing with the spirit of the Platonic solids. And I said, I don't think it's that, but I don't know what it is. And I don't know if it's useful for anything. But that doesn't matter because it's kind of cool, and I like that. And sometimes that's enough. And there's a lot of math that came up just because it was interesting, and no one was thinking about whether it was going to be useful or applicable. Sometimes it takes hundreds of years. There's the famous example of number theory that took hundreds of years before it became the basis of internet cryptography. The Platonic solids themselves, it took 2,000 years. The icosahedron was known just in the minds of imaginative mathematicians. And then 2,000 years later, there were finally microscopes powerful enough to see that viruses often have icosahedral shapes. But in between that, there were no known natural examples of icosahedron. So if we put too much emphasis on math being useful, we can miss things. Plus, it doesn't sound interesting if we say that math is useful. It's like telling children to eat their vegetables because they're good for you. That doesn't make them sound delicious. And if we say that math is useful, it doesn't sound very interesting. Imagine if, would you introduce a friend to someone and say, oh, I'd like you to meet my friend. They're really useful. So moving on now to Battenberg cake, which is one of my favorite kinds of cake. When I'm cooking, my favorite thing to cook is dessert because it has no nutritional value. It exists just to give me pleasure, and I like that. So Battenberg cake is a very English kind of cake. Now that the Great British Baking Show has come across the Atlantic, maybe Battenberg cake is going to be more known over here. But the main point is you have 2 colors of cake, and you definitely don't want the same color of cake to touch the same color of cake, because that would be terrible. But it's also a mathematical structure, because if we take a multiplication table for 1 and -1, then in the top left-hand corner we do 1 times 1, which is 1 usually. We can do then 1 times -1, which is -1. And then in the bottom right, we do -1 times -1, which is 1. So it's a Battenberg cake. We can do addition of even and odd numbers. So in the top left, an even number plus an even number is even. And then an even number plus an odd number is odd. And an odd number plus an odd number is even. And when I do this with my students in class, I then do multiplication of odd and even numbers, and they all go, it's a Battenberg cake. It's not a Battenberg cake. So not everything is a Battenberg cake, but this is a Battenberg cake. We can also do multiplication of real and imaginary numbers. So maybe you don't know what imaginary numbers are. Maybe you've forgotten what they are. Maybe you haven't ever met them before. Imaginary numbers are that thing that happens when they tell you in school you can't take the square root of a negative number, and then the next year they say, now we're going to take the square root of a negative number. But the point is that they're a Battenberg cake. If I tell you that, then you know that a real number times a real number must be real, and a real number times an imaginary number is imaginary, and an imaginary number times an imaginary number is real, because it's a Battenberg cake. There is also, okay, you probably recognize this as cyclic groups of order 2. It's the Cayley table with the cyclic group of order 2, otherwise known as a Battenberg cake. So there's another Battenberg cake about tolerance, because we get ourselves sometimes tied up in knots. If we're trying to be tolerant people, does that mean that we should tolerate intolerant people as well? So I think it's a Battenberg cake. I think that if you're tolerant of tolerant people, then you're definitely tolerant. I think that if you are intolerant of tolerant people, then you're intolerant. But crucially, I also think that if you are tolerant of intolerance, then you are contributing to intolerance, and that is part of intolerance. Whereas I think that if you are intolerant of intolerance, that is part of being tolerant. I think it's a Battenberg cake. So this is related to mattress flipping, which is why I've given everyone a mattress with A, B, C, D on it. Of course, we all write A, B, and C, and D on our mattresses, right? This is the problem with real-life math problems. They're often extremely contrived, and everyone can see through them. And my friends often send me their children's math homework and to show me how ridiculous it is. And one of my favorites is the one that says, you have 1 meter of string. You use 0.3 of it to tie up Sally. And you use 35% of it to tie up Eddie. How much do you have left to tie up Joe? And apart from the question of why we're tying people up, in the first place, 30 centimeters of string is not really very long to tie someone up with. So this is a ridiculous question, a bit like the ones that say, you buy 87 watermelons and you eat 16 of them. So mattress flipping is what you're supposed to do every season to stop your kind of fat bottom from pressing into the same part of the mattress every year. I never do it because I'm much too lazy. Someone pointed out to me that if you have a fancy foam top mattress, you don't want to flip your mattress over anyway. But in theory, you could flip your mattress around in order to preserve it. And if you did, you could write A, B, C, D on it to remember where you were. So there are 4 things that we could do. We could do nothing, because you're me, and you're too lazy. You could rotate. So I'm saying rotation is rotation in the plane. You could flip it over sideways, or you could flop lengthways the other way. So we can examine where we get to if we do these things and make a little multiplication table about it. So the top left-hand corner is where you do nothing and then you do nothing again, because you're me, and you always stay in the A position. So I'm calling A the starting position. Then next to that, there's if you do nothing and then you do rotation. So if you do rotation, you get to B. Now starting again in the A position, if you do nothing and then you flip over sideways, you get to C. And then if you do nothing and flop, you get to D. Right. So now going down the left-hand column is where you do the thing first and you do nothing afterwards. And that doesn't make any difference, right? You can do nothing anytime you want. I love doing nothing. So we get the same thing going down the left. Now we can try, say, coming down the diagonal. If we do a rotation and then another rotation, you get back to A. If you do a flip and then another flip, you still get back to A. And if you do a flop and another flop, it's still A. So when you do the same thing twice, you always get back to A, which tells us that you can't just keep doing the same move every season, because you'll just keep getting back to where you started and you'll miss out some other positions. This is a piece of group theory. What this is telling us is that the symmetry group of a rectangle is not cyclic, but it's actually saying that we have to do different moves every season. So we can try combining moves now. We could try doing a rotation followed by a flip, which is going to be here on the second row. So if we do a rotation, followed by a flip, we get D. And then we can do a rotation followed by a flop, a rotation and a flop, C. Then down on the next row, we can do a flip followed by a rotation. So start in the A position again and do a flip followed by a rotation, D. And then at the end, the whole point, because I get to say flip-flop, so you do flip-flop, which is B. And then maybe you can start seeing a pattern emerging. So what do you think is going to go here? C. And what do you think is going to go here? B. Right. Math often consists of spotting a pattern and guessing what's going to happen next. Then, because we're good mathematicians and not people on the internet, we actually check to see whether we're right or not. We could, anyway. We are right. The main question now is how many Battenberg cakes can you see in this picture? So there's definitely 2 here. There's 2 here. There's 1 in the middle. There's some more depending on how you count them. But there's my favorite one, which is the fact that the whole thing is a Battenberg cake, each of whose individual cakes was already a Battenberg cake. Here's one I made. I call it the iterated Battenberg cake, because what we've done is we've iterated the process of Battenbergification. And I'll do questions at the end.
No, it's just really quick.
Go
Why
on.
not call it a Battenberg cake?
Hmm?
Why not call it a Battenberg cake?
Because I don't think that makes grammatical sense. You could call it that, but I like to think about the process of Battenbergification. And Battenbergification is the process where you take 2 things and you just declare that one of them is going to go in this position 1 and one of them is going to go in position 2. And another reason I like calling it the iterated Battenberg cake is to emphasize the fact that we're iterating something. Mathematicians love iterating things. We're basically like small children who like doing the same thing over and over again, if they can. And here, all I have to do is tell you what's going in position 1 and what's going in position 2. So it could be yellow and pink. It could be chocolate and more chocolate, because I love chocolate. It could be a bunny and another kind of bunny. So now I've Battenbergified a bunny. Or it could be one type of Battenberg cake and another type of Battenberg cake to make the iterated Battenberg cake. If you make this cake, you have to cut off so much cake to make it fit together properly that you end up with almost more cut off cake than the actual cake. And then you make lots of friends. So here is one further level of abstraction I can do on this, which is that once I told you we were doing Battenbergification, the process, all I have to do is tell you what goes in position 1 and what goes in position 2, and then we know what the structure is going to look like. So here it could be yellow and pink, light brown and dark brown, bunny 1 and bunny 2, or cake 1 and cake 2. But what is cake 1? Cake 1 is already one of those. Cake 2 is one of these. So now why don't I take the picture for cake 1 and put it where it says 1? And I can take the picture for 2 and put it where it says 2. And now I have the most extreme abstraction of an iterated Battenberg cake. It's a very efficient representation. And it's also another mathematical structure, which is a tree. You may have studied trees. Trees is a tree because it kind of grows from the bottom. It has a root and branches that branch off. Mathematicians get into funny arguments sometimes about which way up trees should go. And some people think they should start at the top and grow down because, I don't know, trees start in the sky and grow downwards or something. But the great thing about abstract trees is that we can read them any way up we want. And we can read them both ways up, actually, at the same time. So this tree, we can think of it as something starting at the bottom and splitting up. Or we can think of it as things starting at the top and being stuck together. So I say that trees come from sticking things together. For example, here is one way of sticking 3 things together, and here is another way of sticking 3 things together slightly differently. And we can see whether we get the same answer. Say, if we do 4 add 4, we get 8, usually, and then we could add 2 afterwards, and we get 10. And usually we have to write this with parentheses, because we're stuck writing our math in a one-dimensional straight line. But it's really about this tree. So on the other side, we're saying add 4 and 2 together first, which is 6, and then we add the 4 afterwards, and that's also 10, with the parentheses on the other side. And previously, we've known this as the associative law for addition, so we know it's the same. It's really about moving a branch across the branching point of this tree. And we're so used to this being true for numbers that we might forget that it's not true in all situations. For example, if you mix egg yolks and sugar together, and then you add milk and you heat it up, you get custard. However, if you mix sugar and milk together, and then you add egg yolks and heat it up, you do not get custard. So these things are not equal anymore. And this is true of many things that are more subtle than numbers. So numbers are mostly just equal or not equal with nothing in between. But once you start studying more complicated mathematical structures, there are a lot of ways in which they could be not equal. And some of them we might want to count as being the same. For example, if you make cake, then the recipe that I grew up with says cream the sugar and the butter together first, then beat in the eggs, then fold in the flour and bake it, and that's cake. But it turns out that actually, especially if you have an electric mixer, you can just kind of chuck everything in a bowl and go, wah, and it's going to be okay, more or less. It depends what you count as the same, right? And in higher levels of math, you get to choose which things count as the same or not, depending on what you're interested in. So here's the way that we just had of moving one branch from left to right. Here are all the ways of making cake by different methods. So I'm not changing the order of the ingredients along the top. I'm just changing the branching of the trees. So this recipe is the normal one at the left. The next one up says mix the butter and the eggs together first. That's quite disgusting. Then you mix in the sugar, but it turns out once you've added the flour and as long as you beat it hard enough, it's kind of okay. So this one at the end says mix the eggs and the flour together, which is also quite strange. But then once you've mixed everything together, it's all right. The one at the bottom is funny because you need 2 bowls. So you have to mix the sugar and the butter together in one bowl. You mix the eggs and the flour in another bowl. If you're as lazy as me, you do not want an extra bowl to wash at the end of the process. So that one might count as actually different. I took all the ingredients for cake into one of my art classes one day, and we made them in all these different ways. And we discovered that it really did all look pretty much like cake batter at the end of it. But we don't have ovens at art school, so we couldn't bake it. However, I did then give a talk at the Culinary Institute of America. And they do have ovens there. And so we did bake it. And what we discovered is that they all came out like cake, but some of them rose a bit more than others. Now, of course, it wasn't a very scientifically controlled experiment. So I don't know if some people just beat harder than others. What I remember is that this one was a bit flat. It didn't rise as much. Whereas actually these two and the end one were surprisingly fine. And this other one was a bit flat too. But it depends. I quite like dense cake. So I don't mind if the cake doesn't rise as much. Whereas if you like really big fluffy cake, then maybe you do. If you don't have an electric whisk, maybe it's definitely harder to do if you don't start by creaming the butter and sugar together. Maybe if you're not doing the washing up, then you don't care if you make extra bowls dirty. Maybe if you are making the cake yourself, then you don't want it to go through a stage where it looks like vomit on the way to being baked. So it really depends, and these are decisions that we get to make in math to create slightly different mathematical theories depending on which things we count as the same in different situations. And actually growing up from children into adults, we change our notions of what counts as the same. Children can be very obsessive about exactly which piece of chocolate cake they want because they know that this one is definitely preferable to that one. Whereas as adults, hopefully we become a bit more relaxed and consider that all the pieces of chocolate cake are more or less the same and it's okay. And we also we hopefully, not everybody does, but hopefully we get better at treating people the same as well. It doesn't mean that people are the same. It means that we should treat them the same because they deserve to be treated as the same. Now, an obvious next question to ask about this situation is, what if I want to make chocolate cake? Because obviously I do want to make chocolate cake. And if you want to make chocolate cake, there's an extra branch that you have to add. Now, this is a pentagon, and it's called the associativity pentagon. It's sometimes named after Saunders Mac Lane, the founding father of category theory. And I didn't see it until I was doing my PhD in category theory. You wouldn't usually see it unless you were doing that. But it's about making cake. And if you make chocolate cake, you have trees with one more ingredient. And you get a shape with one more dimension. So here it is. This is one that someone 3D printed for me. There's a net in my book that you can cut out and make, but someone saw it and made this 3D print. It has 6 pentagons on it that are instances of this pentagon. It curiously has 3 squares as well, which are to do with the fact that if you change the order of where you're doing something in 2 completely separate bowls, it sort of doesn't count exactly. So every time you add another ingredient, you will get another dimension. So the next one up will be 4-dimensional. We don't have 4D printers yet, so I can't show you that one. but you can represent it in different ways. And these are very key to my research in higher dimensional category theory, where things are not properly associative. So you have to understand the sense in which they are not. It's much more subtle than just saying it is, it isn't. And there are many arguments in life that we should have more subtly than yes and no as well. People tend to yell at each other and go, you're wrong, no, you're wrong. Whereas really there is a sense in which things are the same and a sense in which they're different. And we would do a lot better in the world, I think, if we understood the senses in which things were right, rather than just saying yes, no, yes, no. These are called icosahedra because they are polyhedra that help us understand associativity. So finally, what is category theory? Well, there's been category theory all the way through this talk without me necessarily saying so. I like to say that category theory is the mathematics of mathematics because I think it does for mathematics what mathematics tries to do for science and the world, which is study it logically. So if mathematics is the logical study of how logical things work, and category theory is the mathematics of mathematics, then category theory is the logical study of how logical things work. And this may sound very looped up on itself. I quite like self-reference, so I like that. And some people think it's too abstract, and even some pure mathematicians think it's too abstract. Well, it depends what you mean, right? There are appropriate levels of abstraction for different things. And as I was talking about in the session this morning, abstraction sometimes helps us because it helps us encompass more examples into the same idea. Because the more abstract we get, the more things become the same. And that can be helpful. Of course, at some point, we will have to put the details back in and study them as details. But I have this image that it's like shining a light at things. And if you shine the light very close, then you have a very bright light, but a very small area of illumination. And if you raise the light higher, then it gets dimmer, but you illuminate a broader area. And so you get to see more of the context of what you're doing. The important thing is not to say that one is better or the other, but to pick the right level to hold your light for the thing that you're trying to do. And math isn't about getting the right answers. There are no right answers. Math is about understanding things better and exploring different situations in which different things can be possible. And that is the sense in which I think math is useful and important for everybody in the world to get better at. And I hope that we all will. Thank you very much.
Questions? We have time for questions.
An outstanding presentation. I'm very intrigued by it, especially when you got to the custard example. Because what you did there, you had the same ingredient, custard versus no custard. It got me to thinking that 3 times 2 may not equal 2 times 2. 6 may not. So what it brings me to, you have beautifully equated contradiction theory with discoveries within mathematics, be it category theory or otherwise.
Thank you. And I agree, 2 times 3 is not the same as 3 times 2. Because, for example, if you have 3 bags of 2 cookies each versus 2 cookies of 3 bags each, that's different. The 3 bags of 2 cookies each wastes a lot of plastic, whereas 2 bags of 3 cookies each does not. Those things are, there is a sense in which they're the same, but there is a sense in which they aren't. If you've ever tried to teach small children how to add up when they're still using their fingers, if you give them 11 plus 1, they'll put 11 in their head and count on 1, and that's fine. If you give them 1 plus 11, they'll put 1 in their head and go 2, 3, 4, 5, and then they'll get lost on the way, and then they might get it wrong because they haven't figured out yet that it's better to put the bigger number in their head. So those 2 things are different. Associativity, those things aren't equal. If you do 5 plus 5 and then add 3, that's quite easy because 5 add 5 is 10. We all know that. But if you're doing 5 plus 5 add 8, say, whereas if you do 5 plus 8 first, that's hard. That goes over 10. Have to think about that. So the whole point about equations is that they're not really equal. There's something about them that's different. And we benefit from the thing about them that is the same so that we can pivot from one side of the equation to the other and gain a different point of view via the sense in which they are the same. So there's always a sense in which they're not the same and a sense in which they are that we use to pivot. So I like to say all equations are lies apart from the ones that say x equals x. And those ones aren't useful. And I always had students who would write 1 equals 1 at some point during their exams. And I had to persuade them that it is never helpful to say 1 equals 1. It's true, but it's not helpful because we don't gain any insight about anything by writing 1 equals 1. So all equations are either lies or trivial. that's slightly inflammatory. I'll say all equations are hiding some inequality or they're trivial.
How did you make your braid diagram?
Oh, PS tricks.
Oh. Do you have any more details, or?
You mean what the code was? Well, I probably used PS. I either used Bezier curves, which I love, or I used PS curves. I can't remember exactly how I used these ones. If you really want to know, I can look in my code and tell you. But PS curves are quite good, and Bezier curves are very beautiful, I think. Yeah.
Why did you choose to study category theory for your PhD rather than just some other field, like more special about category theory?
So for me, it was very obvious because at every stage of my life, I've wanted to do the most abstract thing that there is. And because I always felt that my why questions weren't being answered by anything else. And I was driven by wanting to know more answers to the question why. And when I was a child, you know how children love saying why, and then you answer and they say why, and then you eventually realize that that can go on forever, and they realize they can put off bedtime by asking why, that they can not have to go eat their lunch, they will delay leaving the house or putting their shoes on. So they do use it as a kind of tactic for winding up adults. But also I was genuinely not satisfied by any why answers until it became mathematical. And then inside mathematics, I was still not satisfied by any answers to that until it became category theory. And category theory, to me, explains very structurally and deeply why things are happening. Then you can ask why things are happening in category theory. And for me, the interesting part of that is that the answers to those questions are also category theory. So it's like a fixed point of why questions. And that's why I study category theory. Yeah.
So to make the cakes, is there like a special pan, or do you just take like strips of different cakes and put them together?
Oh, I do use a special pan because it makes it much, much neater. So you can do it just by making a little wall of tin foil down the middle of your cake, but that seems like too much hassle to me. So I have special cakes with removable inserts in between. I also have an adjustable cake tin that's a square 12 by 12 that has notches in it so that you can put the vertical things anywhere you want. That's pretty useful too.
Other questions?
Yes, one over there.
Can you give a little bit more insight of how you want to reshape the foundation of how we learn?
Sorry?
Can you do a little insight of how you guys are trying to reform the curriculum?
Oh, well, I think that that math currently puts a lot of people off. And one of the key times where it puts people off is around the later parts of elementary school, say 3rd or 4th grade, where you still have teachers who are general teachers who have to teach everything. And general teachers at elementary level are typically not usually math-focused people, because people who are really math-focused tend to get drawn into being specialist math teachers at a higher level. And so if it's people who are not drawn to math, then they don't feel the joy of math in a creative and open-ended way in the way that mathematicians do. Plus, that's fine around kindergarten and 1st grade when you're just kind of playing with blocks and stuff. But then in 3rd and 4th grade, it's already become complicated enough that they're feeling maybe uncomfortable about presenting it themselves. So the best they can do is teach it algorithmically and then hope that no one asks them a difficult question. So if you've ever done teaching and you've had to teach very near the limit of your knowledge, it's quite scary. And I had to do this a lot when I was first teaching, and I was constantly feeling like I was in danger at any moment of being shown up, because I was practically only one day ahead of the students when I'd frantically read the textbook and then have to teach it the next day. So maybe I shouldn't let on this is what we do, but we do. And especially calculus, because I hadn't done any calculus for about 15 years when I first had to teach it. I couldn't remember how to do anything. So it's quite scary to teach it if you don't feel comfortable. Now, I've reached a point where I feel very comfortable. If someone asks me a question and I don't know, then I say, that's a great question. That's fantastic that you have come up with that question. And I think it's a wonderful fact that children are able to come up with math questions that we can't answer. A 4-year-old, I gave a presentation about circles at an elementary school last week, and a 4-year-old said to me, what's the smallest possible circle? And I got myself really confused about whether a 0 radius circle is really a circle, because it doesn't have the homotopy type of a circle. So is it a circle? I don't know. And then I got really confused. So the fact that children can ask amazing, deep math questions is something that unfortunately gets squashed by the fact that teachers who aren't very advanced in math are afraid maybe to nurture those questions and answer. And then children get the idea that math is something that's rigid, where you're only allowed to do certain things. And if they are not that way inclined, then they will be drawn towards subjects where there aren't any right and wrong answers, like writing stories or drawing pictures or painting. And so a lot of my art students, that happened to them. And when I tell them that math is actually open-ended and you can make things up yourself as well, then they wish that they had been told that earlier on, because then they wouldn't have been put off. So children also get put off by things like memorizing times tables, by having to memorize formulae that came out of nowhere and they don't know, by the fact that they can get told they're wrong and they don't understand why. So all these things are things that many educators are trying to change, and to show that everyone can get better at things. It's not that you're bad at math or you're good at math, because that's another very dangerous myth, that some people are good at math and some people are bad, and that if you're bad at it, there's no way you'll ever be able to do it. So there's that, and then there's also the myth of we should tell children how useful it is, because I don't know when any young person ever got interested in anything by telling them it was useful. But that can sometimes take precedence over showing that it's fun and that it's really part of play. And I think that when we become researchers, we just play around with math concepts a lot. And when you're 5, you play around with math concepts a lot. And it's just a shame that somewhere for the whole time in between being 5 and becoming a researcher, you don't get to just play around with math things nearly enough. And so that is another thing that many people are trying to get more of. Yeah.
You triggered a memory of mine when I was a teenager. You said about a 4-year-old asked you about the circle. And I was in a room with a religious leader and a lot of teenagers, and one gal asked the religious leader, "Can God make a rock so big he can't lift it?" See, it's that circle.
Right. Yes, and self-reference produces all sorts of things. Russell's paradox comes from considering something to do with self-reference. And one of the wonderful things about math is that if we produce a question that's actually unanswerable, then we kind of just say it's not math. And then we just don't deal with it. And so that's a fun thing. And my art students get really baffled by this. And they say, "Are you allowed to do that?" And I say, "Yeah, we do that. That doesn't count. We don't want to study it, we just don't count it." And I say to them, you do that too about art. If you look at a piece of art and you think it's rubbish, then you'll go, "That's not art." Yeah.
One quick question. What brought you to the Chicago Institute of Art School?
Oh, that's a lovely question. I love teaching at the School of the Art Institute. It's basically my dream job. And what happened was that I was tenured at the University of Sheffield, and I became very dissatisfied with what I was doing there. I did not feel like I was using the full range of all the things that I'm good at to make a good contribution, because I truly believe, and I've been brought up to believe, that you should figure out all the things that you're good at and then figure out how you can use that to make the best possible contribution to the world. And I just didn't feel like I was doing that, so I was feeling very disillusioned. Plus, the government was deconstructing the education system. I wanted to go back to the UK to contribute to the education system that gave me everything, rather than staying. I was a postdoc at the University of Chicago. So I went back and discovered that they were dismantling the education system and that it was becoming harder and harder for me to contribute in the way I wanted. So I thought about it and I thought, what would I do if there were no such things as borders and visas and stuff? And I thought I would go back to Chicago, because it felt to me like a really good place to make things up the way I wanted to, rather than fit in with somebody else's pattern. And I didn't want to fit in with somebody else's blueprint anymore. I wanted to make up my own way of doing things. So I came back to the University of Chicago for a year, and I gave myself a year to figure something out. And this thing came up at the School of the Art Institute for 1 semester to teach 1 class as maternity cover. I'm not used to there being any women in math departments in the UK, and so I've never even thought of the idea of maternity cover in a math department, but because there weren't any women anyway. So I said, yes, this sounds like my dream job, teaching math to art students, because I'd already written the book, How to Bake Pie, which was my dream of how I would teach liberal arts math if I ever had a chance. And I never had a chance. And I tried to in Sheffield, and they wouldn't let me because they said that was a waste of time. And so the School of the Art Institute is a liberal arts school, and so they teach everything. And so I thought I'll give myself this 1 semester to make them really like me. And they did. So I stayed beyond there, and eventually, after making sure that everything was going well, I quit my job in Sheffield, and now there I am, and it's great. Thank you very much.